Hey there, linear algebros. Got a quick question for you. Where do naughty rainbows go? Prism. But I hear it's a light sentence.
Oh, brother, this guy stinks!
Shout out to y'all. Let's get ready to boss up.
It's impossible to write out all the solutions to a system that has infinitely many, but should we be curious and want to know some points that do work for the system, there would be a way of generating those. Okay, so with that, I'd like to visit a 2x2 linear system here. We got two equations, two unknowns, and the instructions are plain and simple. Solve the linear system. All right, so there are a couple of ways that we can do this. We can use a substitution method. We could use elimination, and there's another way as well. We could use graphing. I would like to stick though to the algebra way of solving these things. Let's take a look at one way of doing this. So we have two equations. Let me indicate the first one as equation 1, the second one as equation 2. I'm going to do substitution, and what that's going to require is isolating one of the variables in one of the equations. And if you look at equation 1, I think the easiest variable to isolate is the variable y. So I'm going to pick on equation 1 where it's 3x plus y equals negative 4. I'm just going to bounce this 3x over to the right hand side to get y equals negative 3x minus 4. And now we're assuming that the variables x and y are the same two variables in both equations. So if we have this expression for y, negative 3x minus 4, what it means for us is that we're allowed to replace 3x minus 4 into the y that's part of the second equation. Now when you do that, you're going to get 6x plus 2 times negative 3x minus 4 equals negative 8. And we'll go ahead and distribute the 2 to clear parentheses. It's going to give us 6x minus 8 equals negative 8. Now the 6x's cancel out, and we're ultimately left over with negative 8 equals negative 8. And there's no more solving that we could do for x. But what we're left with is a true statement regardless of what x is and regardless of what y is. So you could pick any pair, x and y, provided it satisfies the equations above, and it would be a solution. The fact that we get negative 8 equals negative 8, that's an absolute truth here in mathematics, and this would actually imply that there are infinitely many solutions. Doesn't really matter what x and y are. Negative 8 is negative 8. It's not going to change the fact.
Hell no! To the no, no, no! Yeah, to the no!
So this system does have infinitely many solutions. Okay, that's the indication via the algebra. Now, if it were no solution, we would see something like negative 8 equals 5, or negative 8 equals 0, or 0 equals 1. So a no solution case would be, if we had something like, 0 equals 1, something like that would imply no solution. Now, if we were to do this graphically, what we should expect is there to be two lines that are overlapping each other. So what happens if a system has infinitely many solutions, but we want to see just what are a couple of those solutions? What's one solution to it? What's a second solution? What's a third solution? If we're curious about that, then we're going to need something called parametric equations.
Top?
Oh yeah. Oh.
Now, parametric equations give us a way of expressing the solution to a system in a more concrete way. It allows us to write what's called a general solution to the linear system, and in a roundabout way, we are able to use that general solution to figure out some specific examples of solutions to the system. One way of explaining what parametric equations are as well is they're equations that allow the original variables of the linear system to be expressed solely in terms of what's called a parameter. So in essence, what we do is we take all the variables that are part of the original linear system and we create an equation for it using sort of like a third-party variable. And this third-party variable is what we refer to as a parameter. So for instance, if our system involves the variables x and y, then x will be written in terms of a parameter and y would be written in terms of a parameter as well. Typically they're the same parameter that you use, although you get different formulas most of the time. And this parameter is like a third-party variable that is allowed to take on any real number value that you wish. And when we pick on any particular value for the parameter, we get specific values for x and y. And so essentially a parameter helps to determine in a roundabout way what the value of x and y would be as soon as you choose a value for it. So to define parametric equations, there's a little bit of a science behind it. So I'd like to go through that right now. So let's say that we have that equation 3x plus y equals negative 4. Now, reading this from left to right, the variable that comes first is the variable x. And as such, the variable x can be considered what's called a leading variable. Okay, it leads off the equation in terms of the order in which the variables are presented. Whereas the variable y would be considered what's called a free variable. Now, the free variables are what we use to define parameters. Okay, so free variables help you to create these third-party variables. And what ends up happening is that once you've created these parameters using your free variables, you're able to write the leading variable in terms of them. Okay, so for something like 3x plus y equals negative 4, since y is a free variable, we would define that as a parameter. And the most common letter to use for a parameter is t. So knowing that y is a free variable, one step of defining a parametric equation would be to say let y equal t, where t is a parameter. Now, one thing to note is that t can take on any real number. So t, I'm going to write this notation, looks like a rounded out capital E. Does anybody know what that symbol represents? This symbol here is our math notation for is in, also known as an element of.
Surprise, surprise. Surprise, surprise.
And to the right of this is where I'm going to write interval notation for all real numbers. Okay, so essentially what this means is that t can be any real number. And so since t can be any real number, and we write the variables in terms of the parameter t, as we'll see on the next page with the difference system, that would generate infinitely many solutions. Okay, so the infinitely many solutions in this context comes from the fact that t can be infinitely many numbers. So how do you create parametric equations in general? That's what I'd like to address next. Number one, what you want to do is solve the linear system to determine whether parametric equations are even necessary. All right, parametric equations are necessary when you know a system has infinitely many solutions. They're not needed whatsoever if you know that your system has no solution, or if you know that the system has one solution. All right, so that's one thing that you want to be aware of. Then what you want to do is determine your leading variables and your free variables. All right, and here's how I indicate it. Let's go back up to this equation 3x plus y equals negative 4. Since the x came first, I define that as my leading variable, which means that the y is going to be my free variable. So I'll usually point out which variable is leading and which variable is free. Number 3 says all free variables will be replaced by a parameter. All right, so if you find that you have 2 or more free variables, use different letters for them. That way there's no confusion. So maybe TS, R, W sometimes, or even subscript notation like T sub 1, T sub 2, and so on and so forth. Number 4, you rewrite the equations in terms of the parameters. So what happens is once you define your parameters, there's going to be a way of expressing your leading variables in terms of those parameters that you've defined. So 5 is something I just touched on by saying that. Isolate each leading variable to obtain an equation for it. This will be expressed in terms of the parameters. 6 says this process can leave your paper with equations everywhere. So this is just a matter of advice from Mr. C here, just to be organized with your work with parametric equations. It's very easy to get caught up and lose track of the process of defining them. So I'll show you a 3-step process that I do, which really helps us to avoid making that error. So with that, we're going to use parametric equations to describe the solution set of the linear equation. Now, what you want to be in the mindset of here is that you have a system that you've solved, and essentially you've determined in advance that there are going to be infinitely many solutions. So like with the system that we started out with today, we had 2 equations, 3x plus y equals -4, and then the 6x, and so on and so forth. Really, one equation here is a scalar multiple of the other, in the sense that one of the equations is redundant. You can either pick the first or the second one as being redundant, and we essentially can boil this down to a single equation, and we could boil this down to the equation 3x plus y equals -4. So I just want to point out that you can think of these equations as arising, or us arriving at these equations by use of some substitution or elimination method. Long story short, let's assume there are infinitely many solutions here. So going from left to right, the variable x shows up first, so I would define that as a leading variable. The variable y shows up second, so I would define that as the free variable. Now, the free variables are what you're going to use to define your parameters with. So once we've identified those, we're going to start this 3-step conveyor belt process here. I'm going to say let y equal t, okay, and keep in mind t is the parameter. This takes us to a step 2, where we're going to rewrite this equation using t instead of y. So it's going to be x plus 10t equals 2. And this allows us to isolate the variable x, thereby giving us an equation for x which involves the parameter t. The third and final step is just to make a list of your parametric equations. I'll say PEs for short. One parametric equation is created as soon as we've defined a parameter for a variable, y equals t, right? It's kind of like y equals x, that's an equation. Since t is a variable, y equals t is an equation. We also have this one where it's x equals -10t plus 2. So our parametric equations start with x, -10t plus 2, and our variable y equals t. So you'll notice that by using this third-party variable t, x and y are no longer linked together in a single equation. It's kind of like we've busted the equation up in a way that x gets its own equation and y gets its own equation, and both equations are using the parameter t. Now, why is this helpful? Well, one reason why it's helpful is that as soon as you pick a value of t, you almost immediately get values for both x and y. In fact, if you wanted to, you can construct a table where we can pick some random values of t, and depending on the value of t, we'll get a value of x. We'll also get a value of y. And as an added bonus, we would get an ordered pair that would be a solution to the system. Would anybody like to pick a random value of t for us? 0. Okay, let's use 0. Yep. So we would plug 0 into the t for the equation for x. That's going to be -10 times 0 plus 2. That means x is 2 and t is 0. And when t is 0, y is automatically 0. So one of our solutions to the system would be 2, 0. Not the only solution, because you could pick another value of t. 3, okay. So if you plug 3 into the equation for x, that's negative 30 plus 2, giving you negative 28. Y equals t would be y equals 3. And here's another solution to the system, negative 28, 3. You could do something like negative 1 if you wanted. Okay, that would make x 12, y negative 1, and you get another solution to the system. And there are lots and lots of more values that you could pick for t, since t is allowed to be any real number, which means that there are lots and lots of solutions to the system, i.e. infinitely many solutions. So if it were no solution, at some point, we might see something like 2 equals 3 if we were to solve the system. So that would imply no solution. If it were one solution, then we'd be able to come up, or we would only be able to come up with a value for x, say x equals 1, and only one value for y, so like y equals 2. So there would be no need to define parametric equations for something like 2 equals 3 or something like x equals 1, y equals 2 when we just get one solution. So with part B, let's assume that we were solving a system and we found out that this was really the only equation that you needed for your system. That is, like, the other two, however many other equations you have, are redundant. We're assuming infinitely many solutions, and so we're going to write parametric equations for this equation. And going from left to right, x would be our leading variable, y would be our free variable, and so would z. Z would be a free variable as well. So in this instance, how many parameters do you think we're going to have to define? 2, yep. So for this three-step process here, I'm going to say let y equal t. Now, we also need a parameter for z, and we should use a different letter. And I know this is not in alphabetical order, but I'm going to define z as a parameter s. It's another common letter to use for parameters. This takes us to step 2. What we're going to do is rewrite this equation with our parameters instead of the variables y and z. So we'd have 2x plus t plus 4s equals 1. And what we're going to want to do with this equation is solve for x. Okay, so maybe we'll start off by subtracting those two terms over to the right to get 2x equals, and I'm going to write negative t minus 4s plus 1, and then we can divide everything by 2, and we get x is equal to, let's say, negative 1/2 t minus 2s plus 1/2. So x is isolated, and it's also in terms of the two parameters that we defined. So that takes us to step 3, where we'll just kind of catalog these parametric equations. I'll start off with x. Okay, we found that x is negative 1/2 t minus 2s plus 1/2. In step 1, we saw that y is equal to t. And we also saw in step 1 that z is equal to s. And there they are. Now, it's not required, but if you want to see how parametric equations involving two parameters would work to generate solutions, all it would do is just add another column to our table. So you would need a column for t. You would need a column for s. And then, of course, we'll have columns for the three original variables, x, y, and z. And what these generate are actually ordered triples, because we'll have 3 values due to there being 3 variables, x, y, and z. So when you plot infinitely many solutions with, that are ordered triples, one might expect this to form a plane. which is actually what this would be, geometrically speaking. We saw yesterday that if we add that third variable z into a linear equation, that ups the degree or the dimension of the space, and it would be for a system with infinitely many solutions. Okay. Now, what you can do is just pick random values for t and s and plug them into your formulas to get your values for x, y, and z. So for instance, one option for s and t, or t and s, would be 0 and 0, in which case x would be 1/2, y would be 0, and z would be 0, and so 1/2, comma 0, comma 0 would be a solution to the system. You could use 2 and 1 if you wanted, or -1 and +1. They don't have to be the same two numbers. You could use 1 and -1 if you wanted, in which case if we plug these two numbers into the equation for x, that's going to be -1/2 plus 2 plus 1/2, giving us 2. T is 1, s is -1, and so another ordered triple or solution to the system would be 2, 1, -1. And you can continue picking different combinations of t and s, and depending on what values you choose for t and s, you're going to get a new solution for the system. But I like to just give a little more detail here, just to show you how we could use them to generate the solutions, just so that you have a better understanding of why we're even doing this, first of all. Because to me, I mean, when I was first learning parametric equations, it just seemed a little random, like, why is this even necessary? But obviously now I have a different perspective on it, and so just want to not leave anybody in the dark here. Yep. So with part C, this is kind of a special case here, where we have two equations, and we have three unknowns here, x, y, and z. Now in our first equation, if we wanted to find leading and free variables, I would understand x being a leading variable and us writing down that y is a free variable and z is a free variable. But with this addition of a second equation here, we might have to modify our understanding of what we assign y as, because in the second equation, y is a leading variable and z is still going to be a free variable. Now, if this is the case, all right, if you find that one of your variables is a leading variable in a different equation, then keep that variable as a leading variable, okay? Don't make it a free variable. So what I mean is, we have y as a leading variable in the second equation, but we marked it as a free variable in the first equation. Leading variable will always trump the free variable, okay? So there's really just going to be one parameter that we need for a system such as this, all right? And that would be the common free variable between both equations, and that would be z. All right, so really just one parameter here. We're going to say let z equal t. Now with that, if we rewrite the first equation using t instead of z, we'll still have the variable y in there, but you'll see that that gets taken care of real soon. If we write the second equation using t instead of z, we get y minus 3t equals 1. Now I want to focus on the second equation. The second equation will allow us to get a parametric equation for y pretty much in one fell swoop. All right, just add 3t over, and we get a parametric equation for y. Okay, so parametric equation for z, parametric equation for y. And what do we do about x? Well, what we can do is, now that we know that y is equal to 3t plus 1, we could plug it back into that spot in the first equation. So we would add x plus 3t plus 1 plus 5t equals 2. All right, so let's combine some like terms. X plus 5t plus 1 equals 2. We'll go ahead and isolate x to get x equals negative 5t plus 1. And so at long last, we have a parametric equation for x now. And that's all the variables that we need to write parametric equations for. That's going to take us to step 3. So we'll just kind of catalog these. Oh, I'm sorry. Yeah, I missed that. 8t. That was just an awareness check. No, I'm just kidding. So yeah, the 3t and the 5t do combine to give us 8t. And so we should have x equals negative 8t plus 1. So here we go. X equals negative 8t plus 1. Y is equal to 3t plus 1. And then z is equal to t. And those would be our parametric equations. All right, so I won't do a table for this one because I would like to go on to our discussion on matrices. But do you guys have any questions before we do that? Now, I do want to mention that we could have a line as our solution space, if you will, in three-dimensional space. We'll learn later on, this is kind of a spoiler alert, that when we have parametric equations with 2 parameters in them, that traces out a plane. Whereas a set of parametric equations with just 1 parameter, that's going to trace out a line. And do keep in mind that that's definitely a plausible object to have as our solution, because as we saw, solutions in three-dimensional space could be, one of 3 entities. It could be 1 point, it could be a line, it could be a plane, or there might be some instances where it's the entire three-dimensional space.